We'll save time at the end for the questions. Next up is Jay Lofsted from Atlanta, Sandia National Labs, and HPC Gelato Club. You want PowerPoint, right?
Yes.
Is this yours?
That is mine. Ha. All right. All right, so those that don't know, if you go to LinkedIn, there's HBC Gelato Group, and that is our meetup group for conferences for a social outing that might have frozen dairy. That's optional, but so anyway, we just got back from there. We'll have another outing if we can manage it there this week. So what I want to talk to you about was something that I've been focused on for the last several years now, and that is to make sure that what we do with computational science is actually science, because so much of what we do actually isn't by the definition of science. So previous time I've given a talk like this, it's been much longer, so I might have to rush through this a little bit, so just a little bit of a forewarning there. What we want to look at is that the key thing that we will look at when we're trying to do something that's science is that somebody else needs to be able to reproduce what we do in their own environment. And the challenge, particularly with things that run in HPC, is that we do things on unique or very large custom kind of hardware that other people don't have access to. And if we don't give them some ability to be able to reproduce that in their own environment, then we have something that we say, I got this to work, and somebody else doesn't have an ability to say, yes, I agree that what you did is correct. And because of that, we have a lot of trust, but we don't necessarily have science that's going on. And that's something that, from an education perspective, I think is really critical, not just to make sure that what we're doing is something that is truly science, but from an education standpoint, when you have something that's reproducible, students can then be able to pick it up and work through it themselves. They'll have the answers that they should be able to get to, and it gives them a much deeper experience trying to learn something there. So I'm going to go through some of the things that I've gone through in the last few years to give you kind of a picture on the issues that I've run into and some of the things we've tried to work through. So these are just some of the examples of, for computer science research, the areas that we end up having difficulty is because of all of these different pieces here. For example, if we're having something that is a difficult engineering effort, and that's probably because we have customer new hardware or hardware that's may even not been released yet. How does somebody else come in and say, okay, what you've done there is a really nice advancement making that hardware work and you have some new capability, but they have no ability to judge the correctness of that from a performance standpoint or a functionality standpoint. So is that a scientific result or not? And from my perspective, I look at that and I say it's a great engineering effort, but it may not really classify as science, but you get research credit for it because of the kind of effort that it is. But I want to be able to look at these kinds of things and be able to say, how do we make this work something that then can benefit other people because we have this ability to actually look at it again. One of the bigger difficulties, I know that's really a developing world, not just an African problem, but a developing world problem, is the concentration of resources in, say, China, the United States, and then Western Europe. Is they have such large machines and such amount of resources that they run things on that having an ability to reproduce any of that results outside of those regions can be almost impossible just because the resources physically don't exist. So unless you can get access to them, even if they are reproducible, you may not be able to do that. So that's another factor that needs to be considered as you're looking at these kinds of things. So these are really the kinds of things that ended up being a problem as we start looking at these things. Supercomputing conference, I would argue that most of the work there is not reproducible. I was the reproducibility chair for 2023, and we had one paper that gave us the reproducibility instructions, and they told us how to build the software and get it all set up and get it running. And then they said, let it run for 1,000 hours, and then you'll see the patterns of behavior in the data that we're looking at. And we had 6 weeks to do the reproducibility evaluation on that paper. It's like, there's not 1,000 hours in 6 weeks, so it was completely impossible to do. And those are some of the other issues of trying to validate these things, is we just don't have the time frames when the research is being published to be able to reproduce them, because some of them may be years long kinds of efforts. So that's just another kind of the difficulties in this area. For me, when I look at what the benefits are, these are the things that I look at here. an argument that I have with people that call themselves computational scientists is not that their work is not valid. It's that how do we know we can trust the work? And that's one of the problems that I'm trying to drive in terms of making sure that we have high reproducibility standards. In computational science, while we have a lot of physical things that end up validating things over time, the place that I'm actually having more scary results is on the machine learning side, and I'll show you that here in a few slides. But these are some of the things that we look at as the benefits of doing this work. Now, the problem that a lot of people point at is that, well, putting all that reproducibility infrastructure in makes it a lot longer before I get my publication out, and that's a penalty to me. And I would argue that that's not a penalty, that's an investment that you make to make sure you get a higher citation rate, because you'll end up making the paper a lot easier for people to access, a lot easier to understand, and then more people can pick it up, and then they'll end up citing it later as they do work that builds on what you've done. So that's something that I look at as a benefit of it. And the last one here, this number 5, I think is really the big one, is if you make sure that other people can take advantage of what you've done, your work stays valid and relevant longer. And that's another thing that will help drive citations and build your career as you're trying to help students out. So the question then we have to ask is, how do we actually, uh-oh. It's back, okay. How do we actually support this kind of infrastructure from a publishing standpoint so that people actually have the opportunity? And these are some of the things that you could look at and say, well, are these things enough? And experimental observations for others to analyze, that's for things like bio, where you're trying to just look at how things are growing over time. That's something you would do. Or if you're taking a physical material and applying some force to it, like radiation or something, and the things that happen to that material, those would be observations. And those are things, if you have the right equipment, you could reproduce again, but you'd probably just be giving the experimental observations to people to reanalyze the data. That's normally how that works goes, but you have to give enough of a physical description of how the data was generated so people could potentially generate their own. For a lot of coding things, one of the things that's always desired is have some sort of algorithmic description. And I'll give some information about why that's really not enough either, because saying this is my algorithm doesn't say which variant on that algorithm that you're going to use and some of the difficulties that that provides. Providing code for others to run, one of the things that a lot of people argue is reproducibility these days, that I argue is not, is they provide a container and they say, here, run my container. And my question is how did you build that container? What was your environment? What's the manifest on that? What third-party libraries are you using? And without all of that information, I've been given a black box that I am told is correct and not something that's going to generate just the results that they publish in the paper. So those kinds of things make it a lot more difficult to be able to validate these things. And the last two are really difficult ones because of the custom hardware that we often deal with, particularly on extreme machines. And it doesn't have to be extreme machines. It could also be things like having FPGAs. And unless your machine, your data center has access to FPGAs or particular GPUs, if somebody's doing work that relies on those, you don't have access to that, you can't actually reproduce that result because you don't have access to the right kind of hardware. So the question that then comes up as this last one is, can we get emulators for these things that end up working? And the hardware vendors in general have those emulators, but they're proprietary tools that they do not release to the public because they don't want a third party, such as one of their competitors, having a way to directly benchmark against what they're doing and tweak their designs and make their own versions of things. So these are some of the things that end up being a, hey, is this enough? And the answer is probably not. We had, what really got me started on this, well, I first had a student that started as a database student. They wanted to do reproducibility. I was asked, hey, do you want to work with the student? I said, that sounds like a lot of fun. So we started looking at things and discovered how many problems that we were running into because we were trying to take the Ceph storage system and we had exactly the same hardware 10 years later and access to the authors of the papers, and they still couldn't get the original paper results to be reproduced on the same hardware with access to the original authors. And that's when we realized, okay, this is a much bigger problem than we thought it was. So from that, what I was working on later, and this is a couple of years ago now, we have this SomaSpy application, and what it does is it takes satellite observations of soil moisture, then it takes terrain models, and it uses machine learning to extrapolate the coarse-grained soil moisture observations from space down to much finer grains that they can look at soil moisture for particular regions for things like farming and things like that. And the question that I had, because we were trying to do this as a workflow, is can we reproduce this workflow? And the first question we end up with was, well, the SomaSpy application piece uses machine learning. Is that reproducible? And that went me down a very deep rabbit hole because the answer was in large part no. And the problem that we ran into was all of the machine learning algorithms end up using a pseudo random number generator to generate some initial conditions or some initial data decomposition. And because of that, the values are all over the place. And that's intentional because they didn't want the results to always come back the same. But the problem comes into this. And this is a paper from one of my students, Hannah Ahmed, who's now at UC San Diego. And I said, okay, how much does the randomness matter? And the second one in here from the left, that's the one that to me is the most extreme example. So this is using a neural network and the WIND data set from the UC Irvine data archive that's public. And you can see that the most accurate that the model got was 90%, and the least accurate was down at like 10%. And that is exactly the same data, exactly the same implementation of the algorithm, and all she changed was the random number seed. And if you have that much of a variance in what your accuracy is, when somebody claims my model is this accurate, how do you know that has any validity at all? Because it could be, hey, I got the 90% result, and then you try it later and you get the 10% result, or even if you get a 30% result, then the question is why is this so different? So that led us to try to do some other evaluations that drove down, and we looked at it, and it came down to that there's just not enough information. So one of the pieces that we looked at as part of this is that, okay, well, maybe we can look at and say, people do a lot of machine learning development in Python and then deploy it in C++ because they want more performance. So that should be straightforward because they're both using a Mersenne twister to be able to do the pseudo-random number generation. So we had the same seed that should be the same sequence. And it was not. So that was the next problem. So we can look here, the numbers themselves don't matter, but I'll explain what all the different columns are. So the first column is what the seed value is, and she picked 0 and 42 because those were common values from papers that people use for machine learning. So it was great that we had those seed values. Then the other three were just from the getTime function from Linux. And in the first column, we have just standard Python random numbers, and you can see that the first digit there is a 1, then a 2, then a 2. So that's pretty much all you need to see. And then the second column is NumPy. And again, the same seeds, but it goes 2, 2, and 3. The third column is C++, and it goes 2, 2, 3, but they're different than the NumPy ones. And then she cast it as an int and got a fourth set of the same as the C++ values. So even though we're using the same algorithm from 3 different places with the same seed, we ended up getting different sequences. And so we looked at that and we're like, okay, is this ever going to work? Is this possible at all? And what we ended up doing as part of this project extension piece was that how do we make this work? And the terrifying part is that Python, the first column, this is straight Python, we could never get anything to match it. So I would never use that just because it's completely, truly random and non-reproducible. But what we discovered between the NumPy and the C++ was 2 things. The first one is that if you have the seed and the state, then you can transfer the values between C++ and Python back and forth. But then we ran into a second problem. And I'll just give numbers that are easy. So in C++, you'll get for your output 1A, 2B, 3C, 4D. And then in NumPy, you would get 1, 2, 3, 4. For some reason, NumPy eats every other random number. So if you know this, then you can plan ahead and say, okay, I want this to be portable, so I need to skip every other random number in C++ because we know that NumPy is not going to generate them. And so those are the kinds of things that we start looking at, and it's like, okay, is machine learning reproducible at all? And the answer is, if you're extraordinarily careful and you plan, then you have a chance. The other factor that feeds into this that also should be considered is something like a k-means clustering algorithm. Some implementations have a setup phase where they try some random choices for cluster centroids, and some algorithm implementations do not. And if they do, then they're going to change the random number sequence because they're randomly selecting which one, and you're not going to start with the same place when you start selecting data elements for train versus test. And so that's another thing where you may be able to get the same sequence, but if the implementation of the algorithm is not exactly the same, then you can end up with essentially another mess that you can't reproduce again because everything ends up being mixed up. So this was a terrifying result at first, and then once we figured out how to make it work, it was less terrifying, but at the same time, it said, this is a bigger problem than we really thought it could possibly be. So the question that we're really left with is given these problems with machine learning, how do we make science that incorporates machine learning into science rather than truly, I got it to work once? Because that is the majority of machine learning research these days. And the thing that I would point out is that a lot of people would say, hey, let's just go and give you the source code for everything. And the problem with that is this problem here, this Word2Vec system that came out probably 10 or 15 years ago at this point. And if you're not familiar with this one, this paper published an algorithm that was this word-to-vector algorithm, and they released a source code as well. And nobody bothered to check to see if what the algorithm did matched what the paper published. And people just used the code assuming that it was correct and just built dozens, if not hundreds, of additional papers assuming that they were getting the same results. And then somebody sat down and said, I need to make sure that this is right, and tried to run the algorithm. And when they got to the paper, they ended up discovering, hey, I can't get this to work. And they started digging and digging and digging. And what they ultimately discovered was that the version of the algorithm that was released was different than the one that was used to generate the numbers that were in the paper. And because of that, the paper was actually wrong. But that's a highly cited paper. So they released a correction eventually, which was difficult to get people to accept because they had relied on this so much. And then they had problems with the correction. And that one only took like 2 years to get fixed. But this base version took like 5 or 6 years. And so even if you release the code, you have to have people that are willing to test the code against the output that's being published. So that's another one of these reproducibility issues, is that, sure, here's all the artifacts, but unless they're being verified, you don't know if the artifacts are actually correct. So you can't have it then give that to a student and say, hey, follow this, this is great, because the first thing they're gonna do is run it and then check the results and say, why doesn't this match? And you wanna have that level of confidence in the work that you're doing so that these can be actually useful educational tools as well. One of the pieces in talking with the application scientists that I have over the years, that these are the kinds of things they end up generally thinking about, and I know there's people in here who certainly know more about this than I do, when they want to look at what are the key pieces that matter as far as the reproducibility goes. And there's things like, what's the physics formulas that you're using? And if you know that the formulas are right, then you should be able to get something that is in some way measurably the same. It may not be bitwise identical, but it may be statistically close enough, or some other measure that says that this is the same kind of result. And these are the things that you end up looking at to figure out, is what I'm doing going to generate the same kind of science output or not? And from a computer science perspective, we can look at these things and we may get a little bit uncomfortable because this is a level of abstraction away from the bitwise identical that we would normally be used to. And so these are also things we have to consider when we're looking at the reproducibility, is that we might not say that it has to be identically the same numbers that come out, but we need to say that it needs to be this same physics formula implemented in a way that, based on the discretization, your floating point error, the time step increments, and all these other factors, that it ends up generating something that within some statistical margin of error, it ends up generating something that is considered the same result. So like one of the things that we were doing for a metal-based 3D printing simulation we were working on was to, Sandia has a lot of resources, and one of them is actually a CT machine like you would have for getting scans in the hospital. So they printed out some metal-based pieces, and then they put them in the CT scanner to look at the structure inside them. And they looked at that versus what the simulations are generating, and they said, okay, these are structurally the same, so therefore we know that our simulation is valid. And that kind of validation is great for you to know that what you're doing computationally is the same, but we also knew that we had all of these kind of things right, but at the same time, we may not get identical results out of it each run. It's just that overall the structure and the physical properties of it look the same based on how we were looking at things. So this is another area where we kind of have to look at things a little bit differently to try to figure out what exactly is our standard for reproducibility. Otherwise, we're going to end up potentially going down a road where we're trying to get a level of bitwise reproducibility that doesn't matter, or we end up trying to do something that is a lot fuzzier, but at the same time, we really needed the bitwise reproducibility. We've got to figure out what matters for that particular domain. From a performance standpoint, in my experience, it seems to be there's a lot of work with performance improvements for HPC applications. And while that work is really important, some of the challenges that you end up running into are basically this list of things here. And all of these different things will lead to different levels of variance in what your performance results will be. So one example I can give you that is like the second one here, the simultaneous storage usage interference. A paper that I wrote back in 2009, I was trying to get an adaptive I/O routine that would move where it was writing data based on which storage device was the slowest. So if something was slow and something else was fast, when the fast one finished its work queue, it would steal from the slow ones. And as part of that, to try to forcibly make some of the storage devices slower, I wrote a routine that just did massive data output to one of the storage devices so that I could control, say, this one is being hammered by something else, so it should be the slowest. And what I discovered in my experiments is that as bad as what I had done to that one storage node was, I had places in the actual application runtime that were much worse from other sources. I still don't know what those were, but even though I tried to be something really mean to the storage system, I couldn't be as mean as reality was. So that kind of stuff even then says, like, okay, how do I make something that is closer to reality when you try to do something that's as bad as possible and it's nowhere near as bad as what actually happens? So the other challenge one there, just for broader information on it, is what I discovered is that because the storage system was shared by multiple machines, it was impossible to know where the source of interference was coming from because it could have been completely off the machine that I was on. And it was just that other machine using the same storage nodes. So just the storage would just be slower magically. And it was just a matter of there was no way for me to detect exactly what was happening. So there's all sorts of these kinds of things that end up going. The node jitter usually comes in from things like network traffic. So if you have a network intensive application and you got a lot of packets going out, that can cause interrupts that end up slowing down the application. And those kinds of things are not things that are readily reproducible because it's just the mix of things that are running at the time. So we don't get dedicated system time because it's very expensive. And these are generally multi-user machines anyway. So these kinds of things end up being really difficult for performance optimization. So the last one here is actually another fun one, is that if a CPU gets to too high a temperature, many of them will automatically throttle down their performance because they've exceeded a heat threshold. So if your data center allows it to get too hot, all of a sudden it may throttle down and then your performance drops. And you're just like, what happened? There's nothing that has been different. And then you find out, oh, the temperature got a little too high. And so those kinds of things also end up mattering, and that's completely outside your control. So how do you end up managing for these kinds of things as well? So trying to make these kinds of things reproducible is an extraordinarily hard problem. I don't want to try to suggest that any of this is easy, but it's a matter of the more of this that we can think about and try to manage and try to document, the better chance we have of things being reproducible and usable for other purposes. So I kind of talked about this already, and these are really the three things that come down to why I think that the HPC reproducibility side is a nearly impossible problem. The first one is really that custom hardware and software. Who has 10,000 A100 or V100 GPUs available to rerun tests that, say, Microsoft ran? And the answer is nobody. So that's that kind of result nobody can ever reproduce until that kind of hardware gets so cheap and so available that everybody can buy it. And chances are it will be obsolete and no longer available before it's ever that cheap. So at that point, then it's a, hey, look what I got to work. And you hope that it's something that's applicable to something else. Some place like supercomputing also has, we want the biggest run possible. And for example, let it run for 1,000 hours. It's like, who has 1,000 hours that they can let something run? Or who's going to be allowed to run something like that on a big machine for that length of time? And the answer is nobody. You have to be a system administrator that's able to stick stuff in the back end without permission, really, because it's kind of part of your job. And then you can kind of collect all this stuff passively, but nobody else is going to be able to do that. So that's something else that makes things problematic. So one of the other pieces that ends up coming in that takes us from that pure HPC realm into something that's kind of the opposite extreme, and that's if you kind of look at edge. And all of the edge devices are like your Internet of Things devices, or even just distributed sensor networks where you put something out to monitor an area for fire or something else like that. And these devices end up having all sorts of problems. So like one of the things I ran into several years ago is that a group was trying to take a bunch of small devices, and they had a light that flashed like every second on the device, so they knew they were alive. And they turned them all on at the same time, and they all flashed together. And then the next second, none of them flashed at the same time. They were all off by a little bit. And when the clocks are already off by that much after a second, how do you actually try to keep these things somewhat in sync? So then you have to then put another layer of time synchronization on top, and there's all sorts of issues like that. But then you also have things like battery and the clock, the network conditions. So do you have radio interference in the area that's preventing you from offloading your observations so somebody else can pick it up? Or are you trying to do like a gossip protocol and you end up pushing things and they get pushed to the wrong place and they all back up and then they have to try to drain, but you have no way to drain because you don't have the network connection. All of these things end up causing problems as well. So as much as this is an HPC problem, this is also something that operates across the whole spectrum to this other end where you have more things like edge devices. And so this is something we really need to think about if we want to make sure that the work we're doing is long-term valuable and it's something that can be used for educational purposes. So to kind of bring it to a bit of a close here, these are the things that I've come up with that I look at and I say, how do we do the best job that we can right now? And this is kind of the top 9 things that I've come up with. And number 7 is probably the big one for me, and this is one that I don't think enough people appreciate, and that's use version control for truly everything. If you script everything and then use version control for everything, all of a sudden you have an environment where you can say, hey, I ran this on this date. What version of that script did I use? And you always know that it's there because you never use something that's sitting in the directory. You always pull a fresh copy out of the repo and then you run with that. Because if you just let something sit and then you possibly modify it, then somebody's going to take a snapshot and that's what they ran, and then all of a sudden you don't have something that's reproducible anymore. So making sure that you script it all and then version it all is a huge step forward. Number 4, so Torsten Höfler at ETH, for those that know him, he's gotten a lot of best paper awards and other accolades. And one of the ways that he does that is several years ago, he realized he didn't know much about statistics. And what he did is he went and talked to all the math people at ETH and basically said, teach me the basics of statistics so that I can do better statistical modeling. And he went back then and realized that so many of his early papers were actually bad. So like the one example that he likes to describe is he had a network communication time between 2 nodes on an HPC machine, and it was like 1.4 microseconds or something. But the time between 2 nodes was like 1 microsecond. It's like, how did it get to 1.4? And when he then plotted a distribution of the transfer times, he noticed that it was a bimodal graph. If it was a single hop, it was like 1 microsecond. And if it was a double hop, it was like 2 microseconds. And it just averaged out to like 1.4. But he didn't know it was bimodal until he plotted it that way. And so that's one of the things that also happens very often is that a student will say, well, the statistical method that I know is mean. So I'm going to take the mean of my data, and that is correct. And the answer is, no, it might not be correct. So you need to understand what your data looks like And that's been one of the ways that he's been able to get some real clarity in the work that he does. I'm not saying that it's all correct, but it at least gives more information so that you have a better chance of evaluating it correctly. So, but these are the things I think that really help a lot to be able to get something that works well. So, all right. Thank you all for listening and coming. Yeah.